we're going to work on today is various types of reactions, categories of reactions. And the key to being able to write these and balance them is pattern recognition. Every one of these has a certain pattern to it, distinctive from the others. And if you learn, I guess, for lack of a better word, the definitions of it, then you'll know the patterns and you'll be able to write these without a whole lot of struggle. So the key is learning the terminology and what those terms mean in terms of reactants and products. We're going to start with combustion because combustion is probably the easiest one. Combustion is basically burning things. And for our purposes, when we talk about combustion, this is going to be the definition of it. Combustion means materially, you've got a compound that consists of carbon and hydrogen. I'm using X and Y as generic subscripts. It's either carbon and hydrogen, or maybe carbon, hydrogen, oxygen, but that's the restriction of your elements. You've got something that consists of these elements, and you're reacting it with elemental oxygen, and you form carbon dioxide and water. This is your definition of combustion in equation form. You're always adding O2, you're always forming only carbon dioxide and water, no other products. So I guess in terms of combustion equations, this is your variable, because the rest of it is automatic. Write the balanced chemical equation for combustion of C5H12.
So even if there's already oxygen in the thing, we add oxygen?
Yes, you add more. That's correct. In our first example, balanced chemical equation for combustion of C5H12. In the wording of that question, how many chemical formulas are you told? And don't say one. 4. Because this tells you you're working with C5H12, and this word tells you exactly what you're doing to it. That word combustion means you're adding elemental oxygen diatomic, carbon dioxide, and water are your products. That is the definition. So now you've got all your substances lined out, all you got to do is balance it. So now you start counting carbons and counting hydrogens and counting oxygens and that sort of thing. But if you don't get your formulas set out right, then balancing don't matter. Memorize what that word combustion means in terms of formulas. Question about that? Balancing this one, we've got 5 carbons here, we need 5 carbons there, so we put a 5. We've got 12 hydrogens compared to 2 hydrogens, so we need a 6. With carbon and hydrogen balance, now it's down to oxygen. I've got 10 oxygens in the carbon dioxide, 6 more in the water, so collectively that's 16 in the products. I need 16 in the reactants, and I'd get that with an 8. And that would be your finished, balanced equation. Question about that? All right, do the next one. if you memorize that the word combustion is telling you to add O2 and form carbon dioxide and water, then writing combustion reactions isn't enough. If you don't memorize that that's what combustion means, then you're doomed. Because there's no way you're going to look at CH3CH2OH and figure out what's supposed to happen. You've got to memorize the definitions. Go ahead.
Does that subscript 3 after the H only apply to the A, doesn't apply to the C, right?
Correct. If it had been meant for the C as well, then there would have been parentheses. And there's not. This is the skeleton version of it before doing the balancing. But that's all your proper formulas. What are you going to do to balance carbon?
Put a 2.
2 in front of the carbon dioxide, because you've got 2 carbons over here. You've got 3, 4, 5, 6 hydrogens. So you fix that with a 3 over here. And then oxygens, this is 2 times 2, that's 4. This is 3 more. So collectively, that's 7 oxygens in the products. We need 7 oxygens in the reactants, and this is one of them. So we need 6 more, correct? Which that means 3 there. And that would be balanced. Okay. Question about combustion. About what goes on in a combustion reaction. All right. Now the next 2 types I've got bracketed together here. When you study combination and decomposition, it's probably best to study them simultaneously because they are inherently linked. With combination, you're taking 2 or more substances and unifying them into one. Balanced chemical equation for combination of aluminum and bromine. They're going to go together into a single formula. And you're not told what that product is. And that's okay, because you know about charges. And you know how to look at the periodic table and tell what charges these elements are going to form, and you piece together your product based on charges. The symbol for aluminum is Al. What's the symbol for neutral elemental bromine? Br2. And then we figure out this product based on charge, where aluminum is always a +3 and bromide is what? -1. So pairing off those charges, what's the compound? Good. Al, Br3. And that's all your proper formulas. We still have to do the balancing. Was there any question about that? You got 7 diatomic elements, you got to memorize them. You build that product based on what you know from the periodic table of charges, and you got to memorize those charge patterns. Once you have it to this point, it's just balancing from there. 2 bromine, 3 bromine, lowest multiple is 6. We need a 3 here and a 2 here. 2 aluminums on the products compared to 1, we'd need a 2 here. And that would be balanced. Question? Now the next one is combination of sodium and sulfur trioxide. And this time I do tell you what it's forming. Because it's not a product you could figure out just simply based on charges. In that situation, I'll tell you what the product is. And so in this case, we're forming sodium sulfite. This is sodium. This is sulfur trioxide. Now I'm telling you what the product is, but you still have to piece it together in terms of formulating. That does relate to charges. What's the charge for sodium? +1. What's the formula for sulfite? Sul3. What charge? -2. Sulfate is SO4, sulfite is SO3. So SO3 with a -2 charge, that's the sulfite ion. Electrically, you need 2 sodiums to generate enough charge to match the sulfite. So your product would be Na2SO3. And then you balance. Question?
Is it finished?
It's not balanced yet, no. Question? How would you balance it? 2 sodium, and that would take care of it. Good.
So do we need to memorize all the charges for ions and?
For those common ones, yes. All right, do this next one on your own. Tetraphosphorus hexoxide reacting with potassium oxide. To form potassium phosphite. Combination will always be multiple substances forming just one substance. You combine multiple things into a single thing. In this case, these 2 compounds are being formed into potassium phosphide. Now this one has prefixes. So what's the formula for that compound? 6. Hepta is 7. We're combining that with potassium oxide. Potassium is a +1, oxide is a -2. So what's the formula for potassium oxide? K2O. And then for the product, potassium is a +1 phosphite. Now, as a reference point, what you should have memorized is this being phosphate. That's a very common ion, you're going to see it a lot. Phosphate you should memorize. Phosphite, not so much, but according by the rules of the naming system, that ITE means one less oxygen than the ATE version without changing the charge. So phosphite is going to be PO3, but still a -3. It's an altered version of phosphate. It's derived from phosphate. So this is potassium, this is phosphite, so this is potassium phosphite. Balanced out electrically to be a neutral compound. That's converting all of your compound names into formulas. And we'll do the balancing in a minute. But any question about getting those three formulas? All right. How do we balance phosphorus?
6 by the potassium. Oh, never mind. I was balancing the whole equation.
Oh, well, I mean, for what are you going to do for phosphorus?
4.
4 here. And then, is this the 6 you were talking about? Okay. Yeah, that's right. Okay. All right. What's the question about that? That's how combination works. Multiple things becoming one. Decomposition is exactly the reverse. If you took any one of these reactions that we just did for combination and turned it around, then that would be a decomposition. Decomposition is one thing breaking down into multiple things. And I guess as far as definitions go, when you're dealing with decomposition, unless you are specifically told otherwise, break it all the way down to the individual elements. Sometimes they break down into smaller compounds, and if that's the case, I'll have to tell you. But if you're not told what to form, form elements. Decomposition of sodium acetate. This is sodium. And acetate, there's two common ways for writing this. It makes no difference to me which one you use. But either way, acetate's a -1 charge. So combining sodium with acetate is just a 1-to-1 ratio. This is the sodium acetate, and there is no other reactant. For decomposition, there won't be another reactant. All you're doing is taking that one and busting it up. We're not told what to form, so we take it all the way down to the individual elements. So that's going to be sodium and carbon and diatomic hydrogen and diatomic oxygen. Those two are diatomic, the sodium and carbon are not. And so that's the elemental form that you're going to. putting in coefficients and counting atoms here. I've got 1 sodium compared to 1 sodium, so that looks okay. I've got 2 carbons compared to 1 carbon, so I can fix that with a 2 here. Then I've got 3 hydrogens compared to 2 hydrogens, and that means I got a problem. Because there's not an integer you can put in front of that H2 and have it come out to be 3, correct? Remember, you're stuck with integers. Whenever that kind of thing happens to you, because diatomics will lock you into even numbers. Whenever that sort of thing happens, just kind of back up to the beginning and start fresh, but double what you're working with. And that will guarantee you even numbers across the board. And not necessarily as coefficients, but as far as atom counts, it will. And so it'll erase that problem of odd numbers when you're dealing with diatomics. Now I've got 2 sodiums, so 2 here. 4 carbons, that's a 4. 2 times 3 is 6 hydrogens and 2 oxygens. And that would be your balanced equation. Question? Yep.
So it's not one thing and a 2 thing, it's one thing and a multiple things.
Yes. Decomposition of nickel for carbonate. This is your starting material. Your only starting material. And are you told what to break it down to? Not actually in the problem, no. But I told you 5 minutes ago that unless products are specified, you take it to the individual elements, right? So that means we're going to form nickel and carbon and oxygen. And oxygen being diatomic. And then you would balance it. Question? The next one in the study pack is still decomposition of nickel 4 carbonate. Only this time I give you products of nickel 4 oxide and carbon dioxide. So this time you're not going to elemental form. You're going to the compounds listed. Hopefully you get the idea from this that you need to be comfortable with the naming system. All of you need to practice that naming system, especially in regards to polyatomic anions. That's where most people have the trouble. But if you're not comfortable with the naming system, it's going to cause you to get wrong formulas in your equations. Carbon dioxide is just CO2. Nickel 4 is this. Oxide is this. We're comparing a positive 4 with a negative 2. So NiO2 would be the product. And then balancing would look like this. 2 carbons, 6 oxygens, 1 nickel. Question about decomposition. If you're told what to form, then you form it. If you're not told what to form, it's going to be the elements. All the way down to the elements. All right. Any question about decomposition reactions? Next is single displacement